Thank you, Patrick, for that introduction, and in particular for your plug of my work on quantum mechanics. Just yesterday, I found out that the University of Minnesota um, uh, will not allow me to teach a class that I've been working on for several years, introducing humanities students to quantum mechanics and its history. So I guess it feels a little bit like in the old DDR days, so having a beroepsverbod. Um, but I won't be talking about quantum mechanics today. I'll be talking about COI, which stands for Common Origin Inference, and IBE, which stands for Inference to the Best Explanation. I hope you all had a chance to read my abstract, but let me begin by just giving you a simple example of a COI from like everyday life, right? So imagine that you're trying to park your car in an already pretty full parking lot, but right near the entrance you see like an open spot. Are you going to rush over there? No, of course not, right? You're going to assume that's a handicap spot. Why? Because it would be an amazing coincidence, right? If all those cars that came before you passed up such a convenient spot for no reason at all. Now, that's an example of a common origin inference, right? It's not a coincidence that nobody parked there. The common origin is that it's a parking, that's a handicap spot. And we make such inferences like all the time. Like we reason back from an effect here, like, the spot is empty, to the cause, the spot is a handicap spot. And in everyday life, that turns out to be a pretty reliable pattern of reasoning, right? Now, if you think about it, that's basically because we can rely on a pretty stable network of cause and effect. Now, scientists, and I'll show you some examples, have also had significant success using this pattern of reasoning. But when we're talking about the outer frontiers of science, it's not so clear at all why this should be so successful. And so I've come to suspect that, no matter what they say, that when scientists use COI and IBE, they're actually not making inferences, right? It's not about believing or increasing the degree of belief in their explanations. It's about making the case that the explanation is worth pursuing, okay? And that is what this talk is going to be about. So it's a follow-up to a paper that I published in 2002 called COI Stories. That was a pun on the movie. There's a bunch of case studies. Case studies have become like highly suspect, of course, from the days of like Lakatos and in the 70s. So rather than calling it case studies, I called it COI Stories. And I've been meaning to write the sequel for a long time, and I always felt, I should make it coincide with like one of the sequels to Toy Story, and I haven't quite made it. And as I mentioned in the abstract, I think that inference is in many cases the wrong term. But I want to keep the acronym, right? Otherwise, it's not COI Stories anymore. So I thought about, insight, nah. Intuition, nah. Idea, also no good. Inspiration, a little better. But in the end, I settled on incentive. Okay, so that's what it's going to be. So now, of course, there's a rich history on inference to the best explanation. It's been debated. And basically, the only two words in inference to the best explanation that have not come in for criticism are to and the. So on the E, the question is like, what actually counts as an explanation? And this is where COI has the advantage over IBE, because I believe that, this idea of explaining things by tracing them to a common origin should pass muster on whatever general philosophical account we're going to have for characterizing explanations. Now the B, you can ask, like, what if the best is not good enough? So there, you have to keep in mind that IBE is a slogan, right? The slogan is due to Harman, 65. And the operative notion is just that explanatory considerations provide like a guide to inference, right? And this has been explained very clearly by Mr. IBE, Peter Lipton, now deceased, unfortunately, in his book on the topic. And so then the I, the typical way of posing the question is like, do explanations have epistemic value, right? To put it in more pedestrian terms, does explanatory power affect degrees of belief, right? Should you believe something just because it offers an explanation of something? And so this is where, like Van Fraassen in The Scientific Image has criticized IBE. And in my paper in 2002, I just pointed out that, if you look at the history of science, you can find plenty of examples where, despite Van Fraassen, like scientists really seem to think that works. So again, like, as I said at the beginning, I'm now sort of having my doubts about, like, whether that response to von Fraassen actually works. So a little more about, like, a debate about IBE between, like, Wes Salmon, now also sadly deceased. He inspired this whole COI project with his ideas about common cause reasoning. So this focuses on, like, the question of the B. And so Lipton has this terminology where he talks about the likeliest explanation and the loveliest explanation. What do you mean when you say best? So when you say likeliest, right, I mean, then, like, IBE becomes completely trivial, right? But then it just says the likeliest explanation is the likeliest. So for this to have any teeth, it's got to be loveliest, right, to use. So it's because it's a pretty explanation. That's because you should believe that it's true. And then, like Wes Salmon says, why should that be so? Why should likeliness track loveliness, right? Why should a lovely explanation be more likely than an ugly one? Science is not crime fiction, right? Of course, in crime fiction, think about Sherlock Holmes. This is very true, but why should it be true in science? So as Salmon points out, IBE just gets the relation between explanation and evidence in science wrong. Scientists propose an explanation and then look for evidence for it, whereas IBE is about self-evidencing explanations, right? And so here is an early critic. I wonder whether you can read, when you can guess the source. Aus derselben Theorie erklärt, das ist ein Kunststückchen. Auf diesen Satz folgt nämlich, soweit ich es überblicke, ihr einziger Beweis. And this is from the great philosopher Franz Kafka in Beschreibung eines Kampfes, my favorite piece of his. Now, these philosophical qualms have not stopped some of the greatest scientists in the history of science to use, what on the face of it looks just like IBE and COI. And I'm going to give you, like, two of these COI stories. The first one is about Copernicus. And so here the coincidence is that one of the two major components in the motion of every planet turns out to be in lockstep with the mean motion of the sun. And the common origin is that, like, that's because the Earth and the planets move around the sun. So here's the like a movie of the problem. The problem is called retrograde motion. I hope you've all seen this. So this movie shows you, night after night at 12 a.m. where Mars is. So for the most part, Mars is moving like, east-west. But, every once in a while, right, that's why these things are called planets or wanderers, it goes into the other direction. And then it resumes its normal course. Why is that? So Ptolemy, like, introduced, like, a system of deference and epicycles to account for this. Right? So here's, like, a series of simplified models. Here's the sun going around the Earth. Here is Mercury. So it's two motions, like Mercury moves on a little circle called an epicycle, and that little circle in turn is moving on a big circle called a deferent. All motion here is counterclockwise. And you see that the combination of these two motions would result in retrograde motion. If, like, this motion in the epicycle is faster than the motion in the deferent, you can get this. So you adjust the parameters to get this just right. And you do the same for the other planets. So you do it for Venus, you do it for Mars, Jupiter, and Saturn. And okay, so you can get this to work by choosing your parameters carefully. But there is a puzzle. So one of the two components follows the motion of the sun. So look at this, right? In the case of Mercury and Venus, it's the deferent motion. In the case of Mars, Jupiter, and Saturn, it's the epicycle motion. And Copernicus explains that by saying, well, the Earth moves around the sun. So of course, like, the explanation is very simple, right? So here's the heliocentric model. So here's the Earth. And you see the Earth has sort of the inner track. It overtakes Mars. So from the point of view of the Earth, it now looks like Mars is moving backwards. So how do you get from one to the other? So, if you have to separate now between Mercury and Venus, what we now call the inner planets, and the other ones called the outer planets. So here you have the geocentric model, and now, like before, like Ptolemy only gives you that the sun is in the direction of this line. Now you say, no, the sun is actually in this position. So this now, the sun still goes around the Earth and the planet goes around the sun. This is actually the model of Tycho. But, you can just describe this from another point of view, namely from the point of view of the sun. and then you have the Earth go around the sun, right? So in the case of the outer planets, it's a little more complicated. So again, like the sun should be in this direction. Where is the sun? It's over here. Well, you get the same sort of relative motions if you like change it to this. Now this is still like a geocentric model. Again, this is part of the Tychonic model. But the simple change of perspective, right now you get like a heliocentric model, right? And so to combine the two, right, so this would be Tycho, and now you get like the heliocentric model, you get Copernicus. Okay, so now Galileo, conveniently ignoring like the Tycho model, says like, well, like Ptolemy introduces vast epicycles to explain this, all of which can be done away with one simple motion of the Earth. And then like he adds, right, so through his spokesperson, this alone ought to be enough to gain assent for the rest of the doctrine from anyone who is neither stubborn nor unteachable, right? So I mean, like clearly, like Galileo is talking about belief here, right? You should believe this entire theory just because of this one explanatory feat. All right. So the coincidence, right, to sum up, right, two of the major components like are in lockstep, the common origin, Earth and planets move around the sun. Now the question is this an inference or an incentive? Now I would say like Pace, Galileo, this has got to be just an incentive. Okay, like this idea is completely at odds with Aristotelian physics. It would take a century and a half to come up with the physics like of Newton, right, to fix this up. But at the same time, like, this is a very striking explanation that certainly is pursuit worthy. And like you can see that, Tycho in response to this, like actually adjusted the Ptolemaic system to have that same sort of explanatory advantage, right, as Kepler like clearly acknowledges, even if Galileo does not. So another example I have is core story 3, Einstein versus Lorentz, in case you're wondering about number 2. That's about Newton, Joule, and Darwin. Darwin, I would say, is the absolute champ of inference to the best explanation, and I'll say a little bit about him later, but like I actually stumbled upon this pattern looking in at my work on Einstein. And it's basically like, the very first paragraph of Einstein's famous paper on special relativity on the electrodynamics of moving bodies. So here's the argument. So imagine that you have like a magnet, and look closely. This is only going to happen once. A magnet is moving towards like a conductor with like an ammeter in it, and you saw that as long as the magnet is moving, the ammeter like gives a certain readout. Why is that? Well, standard electromagnetism says that the moving magnet introduces an electric field in the wire. That's just Faraday's law, and the electric field makes the electrons go around the wire. All right, now we do a completely different experiment. We're going to move the conductor with the ammeter to the magnet. Like, look what happens. Okay, so the magnet is now stationary. There is no like electric field induced. But what's happening here is that the electrons in the wire move in a magnetic field, and the Lorentz force coming from that magnetic field makes the electrons go around the wire, and lo and behold, you get the exact same reading on the ammeter. Why is that? Okay, and so if you look at Lorentz's ether theory, right? Well, that's just a cosmic coincidence. Clearly, these cases are different, right? Because there's this one other element, namely the ether, and it makes a difference whether conceptually, whether it's the magnet or the conductor that is moving with respect to the ether. Of course, Einstein says, well, there is no ether, and it's only like relative motion that counts, and so it's the relative motion. That's the common origin here. All right, so Einstein actually talks about that, as I said, like in the very first paragraph of the 1905 paper, right? And I'll read you the German original. Dass die Elektrodynamik Maxwells, wie dieselbe gegenwärtig aufgefasst zu werden pflegt, in ihrer Anwendung auf bewegte Körper auf Asymmetrien führt, welchen den Phänomenen nicht anzuhaften scheint, ist bekannt. And one can ask, is this an incentive or an inference? Okay, so I'm not going to dwell on this too long, but you could see that somebody like Lorentz would not be swayed just by this argument. So I would say like this is probably just best understood as an incentive. Now the argument is made like in other ways. So here, for instance, is like Minkowski making his argument, and he notes that look, there's a coincidence in the Newtonian space-time structure, namely that you have these two operations that leaves like a theory like Lorenz's invariant that seem to have nothing to do with each other, like rotating the coordinate system and setting the coordinate system in uniform motion. And the common origin in special relativity is that these two operations are both examples of the Lorentz transformations, right, that leave them invariant, right? And again, like I'll read you the German original of Minkowski's argument. So führen jene zwei Gruppen ein völlig getrenntes Dasein nebeneinander. Ihr gänzlich heterogener Charakter mag davon abgeschreckt haben, sie zu komponieren. Aber gerade die komponierte volle Gruppe als Ganzes gibt uns zu denken auf. Right? And then a little later in the paper he continues, says that eine solche Ahnung wäre ein außerordentlicher Triumph der reinen Mathematik gewesen. Nun, da die Mathematik hier nur mehr Treppenwitz bekundet, bleibt ihr doch die Genugtuung, dass sie die tiefgreifende Konsequenzen auf der Stelle zu erfassen vermag. And again, you can ask, like, is this an incentive or an inference? Starts to maybe to look more like an inference, but is this in and of itself enough to start believing, or even like increase your belief in the theory? All right, so here's another one, right? You can make this argument in a number of cases. Like now, this is like more like going back to Lorentz and Fitzgerald. Like they realized that in order for things to work out, everything lenses, mirrors, patterns of light and darkness have to undergo that same contraction, right? Is that a coincidence? Well, like of course in special relativity, it's just the space-time structure like tells you that all these systems contract, right? Again, inference, incentive or inference. So Patrick was like referring to this a little bit. So I've been making this argument in a slightly different form, namely that in the ether theory, it's a coincidence that the laws governing matter are invariant under the same transformations as the laws governing the field, right? So these are two parts of Lorenz's theory, right? So you have a mathematical theorem of corresponding states, that says that the Maxwell equations are Lorentz invariant, and a physical hypothesis, which is a generalized version of this contraction hypothesis that says the laws governing matter have that same property. And of course, in special relativity, I shouldn't say of course, because like this is contentious. Well, there's a common origin. They reflect the symmetry of the Minkowski space-time structure. Is this an incentive or an inference? So I argued that this now really we're talking about inference. But, like Harvey Brown, would at best admit that this might be an incentive and would not accept this as an inference at all. All right. So that then raises the question, right? And so even though these scientists are very clear that they're talking about belief, I already quoted Galileo. Here's another a scientist talking about Ewell, talking about COI, but now look, C little o I, so this is consilience of inductions, which belongs, let's say, to the same family, right? Consilience of inductions means that there is a number of evidentiary lines pointing to the same source, right? And so the example that Ewell gave is thus it was found by Newton. That is theory which explained Kepler's third law, explained also his first and second law, although no connection of these laws had been visible before. And then, in a beautiful Victorian sentence, here was a most striking and surprising coincidence, which gave to the theory a stamp of truth beyond the power of ingenuity to counterfeit. All right. So these scientists are pretty adamant this is about belief. Well, how to cash that out, right? So there, you may think, let's turn to Bayes and Bayesianism, right? That's all about how to update your degree of belief in the light of new evidence. And as luck would have it, around the same time that I published my paper, Wayne Myhrvold published a paper, a Bayesian account of the virtue of unification, using some of the same examples that I used, where he gave a Bayesian account. Now that came in for sharp criticism by Mark Lang a year later. And it took Wayne a little while to respond to this, but in the end, I think he came up with a pretty good response to what on the face of it are devastating objections by Mark Lang in a paper in 2017. So here's how Wayne's thing works, right? So here's the, I hope that you've seen like, the basics of Bayesianism before. So here's the rule for updating the belief, right? So here you have the ratio of the posterior and the prior probability, and here you have like likelihoods. What is the probability that you get these two phenomena, P1 and P2, given T, and what is it like, before that? Okay, and so what Wayne now was able to do was he showed that you could factorize the right-hand side into three pieces. Okay, and so the last piece called U is like what he defines as the like my definition is a little bit different, but it amounts to the same thing: the degree of unification of these two phenomena, P1 and P2, provided by the theory T. So you see that the boost for the degree of belief in T coming from those two phenomena is a product of three factors: a boost coming from P1 alone, from P2 alone, and from the unification, right? So this does seem to capture the epistemic value of unification. Now, sadly, I'll show you that this does not work. But so let's apply it now to these examples, right? So Copernicus versus Ptolemy. Let the phenomena be, the P1, the epicycle motion of Venus follows the mean motion of the sun. P2, the deferent motion of Mars, follows the mean motion of the sun. And the two theories are Ptolemy and Copernicus. Now, both the theory entail P1 and P2. Of course, like Ptolemy's theory is carefully constructed to do so. But only T2 explains P1 and P2 by tracing them to a common origin. So the question then is, does this mean that T2 gets a bigger boost than T1? Right? Same question for the Einstein versus Lorentz story. Now the phenomena are like P1, the current when the magnet is moving, P2, the current when the conductor is moving. The theories are Lorentz's and Einstein's. Both the theories entail P1 and P2, but only T2 explains them by, again, tracing them to a common origin. Same question, does that mean that T2 gets a bigger boost? And as you can sort of guess, the answer is going to be no. And the problem is that for any theory T that entails some phenomenon P, whether or not T explains it, the probability of P given T is just equal to 1. Right? So you can just fill in probably P1 given T is 1, probably P2 given T is 1, and probably P1 and P2 T is 1. So you fill that in above, and you see now that, here is U. We can now solve for U. And you see on the right-hand side, like an expression. It's actually kind of mysterious expression. But the important point for my purpose is that T no longer appears in it, right? So the degree of unification here is the same for these two theories, right? And this is like essentially sort of the criticism that Mark Lang, or one of the criticisms that Mark Lang did this. And so if you have like a case of a theory that explains and a theory jury-rigged to give the same prediction, like, this account does not distinguish between these two things. So Myhrvold's response now was to distinguish two senses of unification. So he distinguished between mutual information unification, that's what his Bayesian thing captures, and common origin unification, COU, which is the thing I was talking about. And so Lang's criticism, like rephrased in terms of this distinction, is, and listen carefully, insofar as theories that unify in this my COU sense derive greater support in virtue of the unification they achieve, they do so not solely in virtue of their achieving unification in the Myhrvold MIU sense, and it's the COU sense of unification that is epistemically significant, right? So note that Mark Lang is on the side of, like Galileo, Ewell, saying that this has epistemic value. Now, Myhrvold is saying, no. A Bayesian analysis renders precisely the opposite verdict. When it comes to incremental support, it is MIU rather than COU that matters. Yeah. All right. So MIU gives the same boost in degree of belief to empirically equivalent theories, right? No matter whether they unify or they're jury-rigged to give the same results. Now, Molly Cow, in a very interesting paper, has shown that, like, basically it could be a problem with just picking the examples. If you look at another example, if you look at examples, and she does this for early quantum theory, where you have an embryonic theory that unifies in this COU sense, and there is no sort of jury-rigged competing theory, that there, you can capture the rationality of increasing your degree of belief with this Bayesian machinery developed by Meerwold. Okay. All right. So what lesson do I want to draw from this? Now, the pessimistic gut reaction is that, well, like von Fraser was right after all. Like, explanations do not have epistemic value, right? I could not capture this with in Bayesian terms. And so I've now become very sympathetic to what he says here in the scientific image. He says to accept the theory is to make a commitment to the further confrontation of new phenomena within the framework of that theory, a commitment to a research program, and a wager that all relevant phenomena can be accounted for without giving up that theory. Commitments are not true or false. They are vindicated or not vindicated in the course of human history. All right. So maybe people have said, well, you're giving in to von Fraser a little too quickly, right? And so I could defend myself well, just because one way of cashing out the epistemic value of one explanatory virtue, that doesn't work in some cases, that does not mean that explanation never has epistemic value. It sure does in everyday life. Where would we be without IBE, I ask you? Now, the pessimistic comeback I already indicated at the very beginning. Just because the conditions for wielding IBE in the homely setting are met, doesn't mean they're also met in the scientific setting, right? And this is, like the bitter lesson of the material theory of induction of my PhD advisor, John Norton, right? And I agree with John on that. All right. So does this now deal a knockout blow against common origin inferences and inference to the best explanation in science? And so recall, I can sort of weasel out of this by saying, look, we're just looking at the wrong examples. Like if you look at these examples that Molly Cow is looking at, you can hang on to no, it is about inference. But I want to go the other route. What if it does? What if we just say no, it's not inference? And so, maybe, right, I want to suggest maybe what matters is not what scientists believe to be true, right? That's the epistemic issue, but what they consider to be worthy of pursuit, right? And that's a pragmatic issue. And let me emphasize that pragmatic is not a pejorative term, or, in a better slogan, like pragmatic is not a four-letter word. So in science, I would say, COIs and IBEs are often not inferences. They're not about increasing the degree of belief in the explanation, but incentives to further pursue the explanation, right? So that's why I want to allow the I to stand for inference as well as incentive. All right, so pursuit-worthiness. How we're going to cash that out, right? Why would you devote your limited resources, money, time, and more importantly, postdocs, magister mention, student assistants, why would you do this? And so you can have sort of, be pragmatic with some epistemic residue, right? Where you say, well, where the COI is still at least partly about inference, right? So you believe that the explanation latches onto something in nature, but you remain agnostic about exactly how it does that. Or you can go whole hog, you're purely pragmatic, so it has nothing to do with inference. You just say well, it'd be neat if this explanation were true, right? So I'm thinking about, a famous line by Alan Guth, where he says, inflation looked too good to be wrong, right? It's an argument no, this it's a bit of a joke, but if you interpret it as, well, this would be really neat, we should look into this, right? Then it makes a lot more sense, right? So you decide to find out, and you're going to use other schemes to try and confirm or disconfirm the explanation, right? The sort of thing that Wes Salmon was telling Peter Lipton is what scientists should be doing and are doing. Now I see some advantages of recognizing that this I could be incentive rather than inference. And in particular, it means that I don't have to accuse the scientists in my core stories anymore of jumping to conclusions. Right, so if you think about Copernicus, remember Galileo, you should believe this on the basis of just this explanatory feat. Well, I mean, Kepler had already pointed out that Tycho gives you the same explanatory feat. Moreover, this, as I also mentioned, this heliocentric model completely flies into the face of Aristotelian physics, and it took a long time to come up with the new physics to make that model sensible. And that the same is true for Einstein, right? I mean, Lorentz came back like, look, how are you going to conceive of light waves if you don't have a medium? And it was not just Lorentz, it was also like Einstein's friend Ehrenfest who said this, right? So in an amusing comment in his lecture in 1913, Crisis of the Ether Theory, his inaugural lecture in Leiden, he quipped that to the two postulates of Einstein's theory, we should add a third, to the effect like, we solemnly swear that the first two are satisfactory. So now from a cosmologist at Chicago, Michael Turner, I learned this beautiful term called forward engaged. Forward engaged. I like the term, but I do want to take the opportunity to apologize to Alan Franklin. He was in the audience when I first talked about this, and Alan says like, well, the term sounds too matrimonial to me. And so in my paper, I added a footnote. I said like, thrice divorced Alan Franklin thought it was too matrimonial, right? And Alan has been reminding me ever since that he's only been divorced twice, right? And he's been married to his third wife, Cindy, for a long, long time. So like, I want to set the record straight. Alan Franklin is not thrice divorced. He's only twice divorced. And like his point stands that engaged sounds a bit matrimonial. But I like the term. And basically the idea is that, these COIs, they take an advance on science, physics, yet to be developed, right? And so it's not like some euphemism for arguments that, don't quite make it. It's just another term, yet another term for things being pursuit-worthy. And you see scientists, actually, if you now look, so as I showed you scientists talking about this like in terms of belief, but there's also scientists who recognize sort of this pursuit-worthiness, right? And so I won't read you the whole quote, but this is like J.J. Thomson. This comes from a paper of George Smith. And if you haven't heard, I'm very sorry to be the bearer of bad news, but George Smith passed away like 2 weeks ago. So he quotes like J.J. Thomson and says like, a theory, or and the same thing you can say about an explanation, is a policy rather than a creed. And I really like that quote. And my friend Rich Bellin, like an expert on Darwin and like, history of science in Victorian England, like he pointed me to this quote by Darwin's friend Hooker, where Hooker says, like, I have no formed opinion of my own on the subject, the species. I argue for immutability till I see cause to take a fixed post. And thus you see I'm ever ready to make it, right, his opinion about species, subservient to botany instead of botany to it, as must be the true relation. Right? So to translate the Victorian prose for you, right, what Hooker is saying, like, I'm not doing botany to provide proof for the theory of evolution. No, I'm adopting evolution because it allows me to do better botany. Now, what about Darwin himself, right? I already told you, like, he is the champ of the IBEs. And so there is like, the various chapters towards the end of the Origin, like I have my students like analyze this, are rife with IBEs and COIs, right? And so the strategy is to just display a wide range of facts that are extremely puzzling from the point of view of special creation, but are readily explained in Darwin's theory. And so they clearly are meant to provide evidence for the theory. But you have to be careful. So Darwin's theory posits three things: descent with modification from a common ancestor or ancestors through natural selection. And most of these arguments only support A and B and not the theory of natural selection. And Darwin, if you look at it, so if you look at the most common edition of the Origin, the 6th edition, he overstates his case. So this is like very sort of Orwellian, where Darwin writes, it can hardly be supposed that a false theory would explain in so satisfactory a manner as does the theory of natural selection the several large classes of facts above specified. He was more careful in the 1st edition, where he clearly, like, I won't read you the whole quote, but now he doesn't say the theory of natural selection, but the idea that they're descended from a common parent and modified, right? So now he does say the two elements that are actually supported by these arguments. But if you look further, you see that Darwin also like has an eye for like the pursuit-worthiness of the theory, right? So this is like a quote from chapter 14 in the first edition. He says, when the views entertained in this volume on the origins of species are generally admitted, we can dimly foresee that there will be a considerable revolution in natural history. Systematists will be able to pursue their labors as at present. So initially, it's a bit jarring. So like, didn't you just say there would be a revolution, and now, you say it's business as usual? Here comes the catch, but they will not be incessantly haunted by the shadowy doubt whether this or that form be in essence a species, right? Again, like Hooker was saying, you can use this theory and do better biology. And so I just want to quote, and I have from a award-winning paper by my friend Rich Bellin. And so here is Rich himself, like, reading this to you.
Darwin hoped that working naturalists would embrace evolution after The Origin appeared in late 1859. He was disappointed. His evolutionary ideas made painfully little progress in the scientific community. But by 1863, the tide had turned dramatically, and within 5 years, evolution became scientific orthodoxy in Britain. The Origin's reception followed this peculiar trajectory because Darwin had not initially tied his theory to productive, original scientific investigation, which left him vulnerable to charges of reckless speculation. The debate changed with his successful application of evolution to original problems, most notably orchid fertilization, the subject of a well-received book in 1862. Most of Darwin's colleagues found the argument of the Origin convincing when they realized that it functioned productively in the day-to-day work of science.
See, there you have it. Don't take it from me. So now the question becomes like, well, how do you find evidence, right, for these common origin explanations, if not through common origin inferences? And so, I mean, there's like many ways. I've been interested in one particular way to do this, and I have 3 examples, like Newton's theory. I'll talk about this very briefly. The Hockney thesis. This is the thesis that Renaissance painters achieved greater realism in their paintings by using optical aids. And a topic dear to Patrick's heart, inflationary cosmology, right? The idea that the very early universe went through a period of exponential expansion. And so I want to start with Newton. And so here, like I said, there's a COI element, right? So you've all heard, like, the story about the falling apple, right? And the idea that, well, the force that makes apples fall on my head is the same force that keeps, like, the moon and the planets in orbit. And like, like one of the rules of reasoning in the Principia sounds an awful lot like COI, right? Causes assigned to natural effects of the same kind must be, so far as possible, the same. Now, so what is the evidence? Well, like, the evidence is that, like, you can get Kepler's 3 laws of planetary motion, right? I showed you this comment by Ewell. So Newton called this deduction from the phenomena. This has been glossed in all kinds of different ways. So Ewell glosses it as an IBE, more specifically as one of his conciliants of induction, which I argued is a family member of COI. George Smith, and in his wake, Bill Harper, gloss it as, slogans like turning data into evidence and agreeing theory-mediated measurements of parameters. So in the interest of time, I'm not going to elaborate or explain these slogans. I just want to pick up on an idea that they also, like, that I got essentially from them, and that is basically so that Newton, like, the really good evidence for Newton's theory is not that it explains, like, Kepler's laws, but that it also explains the deviations from Kepler's laws, right? And so in the 18th century, like, they're now trying to calculate, like, like, you get perturbations from planets that would lead to deviations. Newton knew this, but established that the effects would be too small. But now, like, you have better observations. You have, like, you can calculate these things. And so, one of the famous things is, like, you notice irregularities in the orbit of Uranus, and it turns out that is explained by positing the existence of a new planet, which is then discovered. So they tried this again. Now you have irregularities in the orbit of Mercury. So like, now like a new planet was introduced, like Vulcan. And as I like to say, like, that planet was not discovered until like Mr. Spock, joined the Captain Kirk on the Enterprise. So here Newton's luck ran out, and we have like, Superman Einstein coming to the rescue and really changing like, gravitational theory. So what do we learn from this sort of like evidential history? So, like despite all the evidence amassed for the theory, no, gravity we now think is not some mysterious action at a distance, right? That is culture, not nature. Um, the current idea, like it's space-time curvature, who knows whether that will stand. But there are things we did learn from the ages, right? We did learn to use Plato's phrase, like a new way of carving nature at its joints, new groupings of phenomena into natural kinds of phenomena kinds, like to use a phrase that Laura Snyder introduced. So we've learned for the ages that there is no distinction between sublunar and superlunar space. And we know that whatever keeps planets and moons in orbit is the same as what makes apples fall and pendulums swing. And so we have discoveries like, they were made guided by Newton's theory, like think about Neptune. And so, of course, we can no longer use it as a guide at the research frontier, but we can still use Newton's theory for practical purposes, right? It's good enough to find our way to the moon, even though it's not quite good enough to find your way around town. GPS, you need to put in like GR corrections. All right. So there's something similar going on with the Hockney, or like more appropriately called the Hockney-Falco thesis, right? So this is in Hockney's book Secret Knowledge, discovering the lost techniques of the old masters. And so there's a very similar thesis about Vermeer, that he used the camera obscura. That has been widely accepted thanks to like work among others by Philip Stedman. The controversial part is that this goes back way earlier, that Van Eyck, Lotto, Caravaggio, other Renaissance painters already used these optical devices. And now Hockney just did this by eyeballing. And I think the high quality evidence is actually supplied by the physicist Charles Falco. And it's the same sort of thing that we saw with Newton, that the best evidence is not like, oh, this looked very lifelike. No, there's sort of where there's deviations from this sort of ideal. That's what's telling. And here's an example of this, and I'll let Charles Falco, he posted a little movie that I'll play for you where he explains this. So this is like a portrait of Cardinal Albergati, and so this drawing here matches this painting almost perfectly, but it's like it had to be scaled up a bit, and in the scaling up there's a little bit of a strange error. And so one option suggested by Hockney was, well, he bumped the easel, which is not a very plausible one. Here is like the much more plausible explanation found by Charles Falco.
On the stand is a life-size copy of Van Eyck's Cardinal Albergati drawing. To enlarge the drawing by the necessary 40% to the size of the painting, the image is reflected and focused by a concave mirror onto the floor. Because we're dealing with magnifications greater than 1, even the highest quality concave mirror will only focus with high fidelity a portion of the drawing. Here John is painting in the portion of the drawing that is focused with high resolution. We jump ahead and he finishes the red region. Now he moves the drawing so the top of the head is in the high fidelity region projected by the concave mirror, and then moves the painting to match the new high fidelity region, which is the top of the head. He starts to paint that in. We jump ahead and finish that region. The back of the head is too far away from the central axis of the mirror to get into proper focus. To get around that, all John has to do is turn the drawing around. Put the bottom part of the image in sharp focus, slide the partially completed painting into position, and now paint the lower part of the ear and the collar. We jump ahead to finish that. Move the drawing one more time. Move the painting to match the drawing. Finish the top part of the ear and the remaining part of the head. We jump ahead to finish the head. And now John overlays the 40% enlarged painting onto a life-size copy of the Cardinal Albergati painting that we have in my lab, and we see the fit is excellent. We have 4 regions within each of which there is extremely high fidelity, and each of the 4 regions is displaced from each other by the necessity to translate the drawing in the painting because of the optical properties of a concave mirror.
Okay. Right. So as somebody attending like one of the symposia about the Hockney-Falco thesis pointed out, like Ellen Winner, she said, like, Hockney and Falco are not saying lenses are the only way to get the perspective right. They're saying lenses are the only way to get the perspective wrong in precisely the ways these artists erred. And I think, like, this is like very strong evidence, and I hope you see sort of the analogy with how you get like evidence for Newton's theory. And I think in inflationary cosmology, you see a similar sort of thing, right? So Alan Guth has this COI idea. It's not an inference, right? The exponential expansion of the very early universe would explain some puzzles, the horizon problem, and the isotropy of the cosmic microwave background, the CMB. And so here's like an early heat map of the CMB. This is the cosmic microwave, but the cosmic background explorer, COBE, in 1990. And you see, like, this, if you compare this to a heat map of the Earth, this is incredibly like uniform, isotropic, around 3K. But the better evidence actually comes when you look more closely, and there you see sort of a tiny anisotropy of the CMB. So generic inflationary models predict these temperature fluctuations around 3K with a particular signature. And they are found in these later measurements. The WMAP, the Wilkinson microwave and anisotropy probe, and Planck, the guy who found the formula for black body radiation, so very appropriate that it's named after him. So they show this. Now, should you therefore believe in inflation? Well, not so fast. I mean, it's still completely unclear how to connect the mechanism of inflation with like known physics. But surely, like, you have very good grounds to continue pursuing this theory, right? And as I mentioned, so Patrick, together with William Wolff, has a paper on this coming out in the British Journal for Philosophy of Science, The Virtues of Pursuit-Worthy Speculation, The Promises of Cosmic Inflation. All right, so I'll wrap up. So I've now come to believe that the I in COI typically stands for incentive rather than inference. And and that move from inference to incentive can be used to answer Wes Salmon's question to Peter Lipton about IBE, right? I mean, why should a pretty explanation be more probable than an ugly one? Why should likeliness track loveliness? Science is not crime fiction. And if I allow the I in COI and IBE to stand for incentive as well as inference, you can take the position that it's pursuit-worthiness rather than likeliness that tracks loveliness in science. And that, I submit to you, is a much easier line to hold. And with that, I'll close the book on COI for now. Thank you.